One of the biggest tasks we set out to accomplish in our study of algebra is to generalize patterns and relationships that we see in numbers, whether in pure mathematical contexts or in application to problems in the world around us. Understanding the numbers themselves to which these patterns and relationships apply is a foundational component toward the construction of our algebraic knowledge, and understanding these numbers is exactly what we seek to do in this lesson. Our goal is to classify real numbers, and by classifying, we mean to arrange things into categories based on common characteristics. You are already aware of different ways we might classify or categorize numbers. For example, even numbers versus odd numbers, prime numbers and composite numbers, numbers that are positive and numbers that are negative, numbers that are perfect squares, etc. When referring to classifying real numbers, the categories into which we usually sort these numbers are most often the categories I am about to detail now. Where I want to begin is by giving you a visual depiction of what the real numbers are, and I'll do so down here. So the real numbers definitely include the numbers that are labeled on this number line, but that's not just it. The real numbers also include all the numbers in between. So like 1.5 is going to be real, and pi, it's really the entire number line extending toward negative infinity and towards infinity. So really, we can think of the real numbers as numbers that we can use to measure things like distance or temperature or whatever it might be. Things that are going to have some sort of a physical meaning. So we can imagine that this rectangle here is going to be like the universe of all of the real numbers. So in other words, we're going to be able to contain all of the real numbers inside of this box or this rectangle. What I'm going to do is I'm going to break up this box into two boxes because we have two broad categories of real numbers that we can break the real numbers into. Now, just because I made one of these smaller boxes bigger than the other box does not mean that there's more numbers in the first category than in the second category, because that's not true. I just need to write more stuff in the box that I made bigger than in the box that I made smaller. So just kind of keep that in mind. Now, in the box that I made bigger for this category, there's going to be some smaller subcategories that we can break this category into. So I'm going to draw 3 more smaller subcategories, and we'll talk about what those categories are a little bit later on. Alright, so let's introduce the first main category that we can break real numbers into, and that would be numbers that are rational. What it means for a number to be rational is exactly what the first 5 letters of rational spells. It spells the word ratio. And what it means to be a ratio is that we can compare two numbers, or in other words, write numbers as a fraction. So that's exactly what it means to be rational. I'll say that again. Numbers that we can express as a fraction. So the way that I will kind of denote that is it's numbers that we can write as some number a divided by some number b, right? Because that's a fraction. Now the thing is that a and b, they can't just be any numbers, because really to be a fraction, you're not supposed to have decimals in the numerator nor in the denominator. So what I'll say about that is where a and b are integers, because those are numbers that don't have decimals. So like for example, like if you had this number right here, 0.7 over 4, like it looks like a fraction, but really technically it's not. Like you'd want to try to find an equivalent fraction to that where there's no decimals in the numerator nor in the denominator. So we want them to be integers. We'll talk more about integers later on. The other thing that we would want to make sure happens with rational numbers is that b should not be 0. Because if that number right there, the denominator of the fraction, was equal to 0, then you wouldn't really get an answer, because anytime you divide by 0, that's undefined. Some examples of numbers that are rational. So I'm just going to write some examples of numbers off to the left side there. 3/4 is rational. We could also have like -8/5, also rational. Very clearly, they're fractions that don't have any decimals in the numerator or denominator, right? I'm going to write a couple more examples, 1/3 and 2/7. So one thing that's going to help us distinguish rational numbers from the other category that we'll get into a little bit is understanding the decimals that we get when we turn rational numbers into their decimal form. So I'm going to do that with these examples that I just created right now. So with, oh, I erased it there. Okay. So with 3/4, it's 0.75, right? And with -8/5, it's -1.6 as a decimal form. And then 1/3 is 0.33333, repeating. And then with the 2/7, it turns out that it's 285714, 285714, 285714. And well, what you'll notice there is there's those 6 digits, 285714, that keep repeating themselves. So we could actually just write this a little bit more abbreviated and say that it's like that, and put the bar over all 6 of those digits there. So it turns out that if a number is rational, so a number that we're able to write in a fraction form, either this type of case will happen with the decimals, or this type of case will happen with the decimals. And what do I mean by that? In that first case right there, the decimal stopped. 0.75, and then it stopped. Or -1.6, and then it stopped. Or in the second case, the decimals actually go on forever, right? It'll never end. But the important thing also to notice is that there was some sort of a chunk of digits. So like in this case, there was one single digit that kept repeating itself, or there was a chunk of 6 digits in that case that kept repeating itself. So those are the only 2 things that are going to happen with rational numbers in terms of looking at the decimals. We'll summarize that come in a little bit later. The other category that we'll move to now, that we can break real numbers into, is numbers that are irrational. So obviously irrational numbers are going to be the opposite of rational numbers. So if being rational means that we can write it as a fraction, then irrational numbers are numbers that we are not able to write as a fraction. So in other words, there is no whole number divided by a whole number that will equal these irrational numbers, right? So yeah, just very simply, you're not able to express as a fraction. That's what an irrational number is. So let me give you some examples. Pi is a pretty common example. You can come up with fractions that get you really close to pi, like 22/7 gets you kind of close to pi, like 3.14 at least. But there is no fraction actually that can equal pi itself. We know that pi is 3.14159, etc., right? What are some other examples? This is a good example right here. So if you had, let's say, like 0.25, 255, 25555, 25555. So basically what I'm doing there is you have these 2's and then 5's between them, but I kind of keep increasing the number of 5's that fit between the 2's, right? It turns out that that's irrational as well, and we'll talk about why that is a little bit later. And then the last examples that I want you to be familiar with would be the square root of 2 and also the square root of 3. Those are irrational, but not the square root of 4. The square root of 5 is, the square root of 6 is, the square root of 7 is, the square root of 8, but not the square root of 9. Okay, so let's talk about why that is right now. So why did I skip the square root of 4? Well, it's because the square root of 4 is 2, right? And then the square root of 9 is 3, and also I guess we could do the square root of 1, which is 1. So with these numbers that I wrote right here, they all came out to be nice whole numbers, and we're always able to write them as fractions. They're all rational because this is 1 over 1, right? And 2 is 2 over 1, or if we want to get fancy with it, right, we could write it as 8 over 4, and 3 is 3 over 1, or whatever, right? So those are all actually rational numbers when we take square roots of 1, 4, 9, and then the next would be 16, because the square root of 16 is 4, and then 25, because the square root of 25 is 5. But otherwise, if we square root any other whole numbers, so 2, 3, and then 5, 6, 7, 8, and then we can do 10 all the way up to 15, because then 16 is a perfect square, so then we can do 17 all the way up to 24, because then 25 is a perfect square, and we can start at 26 and go all the way up to 35, because then 36 is a perfect square. Turns out that these are all irrational. So I'll talk about what we're going to see in the decimals of these numbers in just a little bit. So let me now really explicitly tell you, how do we actually tell if a number is rational or if it's irrational? And this is exactly how you can tell the difference. So if a number is rational, there are two different cases that might happen. They both can't happen at the same time. So it's either got to be option number 1 or option number 2, but these are the only two options if it's rational. So option number 1 is that the decimal is going to possibly terminate. And what terminating means is the decimal has to end. So, for example, the number 5/8, suppose, which if you turn it into its decimal is 0.625, its decimal stopped, right? So that would be an example where we would have a rational number, right, because it's written as a fraction, where the decimal stopped, it terminated. So we get that to happen. The other possibility is that the decimal is non-terminating with many rational numbers. And what it means to be non-terminating is it means to be non-ending, right? Because terminating means to end. So in other words, non-terminating is going to go on forever. But it can't just go on forever. There needs to be a repeating, I'll call it chunk of digits. And what I mean by that is, like, by example of what was going on up here and going on over here, when I gave those examples of 1/3 and 2/7, is repeating the same sequence of digits over and over and over. I'm kind of running out of room, so I'll just write an example kind of to the left of number 2 right there. So another example would be like if you had 3/11. 3/11 is 0.27272727. You keep repeating the same sequence of 2 digits in that case over and over and over. So those are the only two possibilities for rational numbers. For irrational numbers, there's really kind of one description we can give to irrational numbers, and that's to say that the decimal is always non-terminating for irrational numbers. So what that means is that the decimals are always going to go on forever for irrational numbers, and there is not a repeating, using my same kind of vocab or lingo from before, not a repeating chunk of digits. So let's exemplify that up here with my examples. So right there, I give the example of pi, and it's going to have 14159, goes on forever. Irrational numbers always have to do that, but then it's just random from there. It never repeats like numbers over and over again. It's just very random. Now, here, it looked like there was like a pattern, but it didn't actually repeat the same sequence of the digits over and over and over, because it was like 25 and then 255 and 2555, right? So it turns out that this number, there is no fraction that you can write to equal it at all. So it's an irrational number. And then with all of these square roots of non-perfect squares, there are no fractions that you can write to equal them. So when you look at the decimals for these, so like square root of 2 is like approximately 1.41, but it's not, because it actually has decimals that goes on forever, and it's just very random. And the same thing for square root of 3. It's like 1.73, and then it like goes on forever. So next, what I want to do here, now that we've kind of distinguished between rational and irrational numbers, is just introduce the smaller subcategories that we can break the rational numbers into. So next, after we've categorized a number as rational, we might break it into a smaller category that we call the integers. And integers are just very simple. It's just -3, -2, -1, 0, 1, 2, 3. So there are no decimals in integers. They're just counting numbers that are either negative or positive or the number 0. That's all that integers are. And then after we've broken numbers into integers, we might be able to say that maybe it's actually a whole number as well. Now be careful, because oftentimes when we use the term whole numbers, we often might mean numbers that don't have decimals. And while that's going to be true about whole numbers, technically whole numbers really, truly are just the counting numbers that start at 0. So again, whole numbers don't have decimals, just like integers, right? Because whole numbers are inside of the integers. But whole numbers are going to start at 0. So whole numbers don't have any negatives at all. And then finally, the smallest category that we will break the rational numbers into is the natural numbers. And natural numbers are counting numbers that start at 1. So the green and blue categories are almost the same thing as each other, just the only difference is the whole numbers include 0, and the natural numbers do not include 0. So just to kind of bring a little bit of summary to what I just showed you there, kind of on a number line, the integers are going to be these numbers on the real number line. So just numbers without decimals, but in the negatives and 0 and positives, right? And then I just introduced also the whole numbers here for you. So the whole numbers are going to start at 0 and then go on forever, right? Again, no decimals. You can kind of think like whole includes the letter O, which looks like a 0, right? So that can kind of help you maybe remember that whole numbers includes the 0 or starts at 0, right? And then the natural numbers, they start at 1.